You train on Fourier-based graph convolutions. They hit walls with long-range signals. You train on wavelet networks. They fumble short-range precision. You realize they share abstractions. Spectral bases adaptability, kernel expressiveness, multi-scale mixing. You merge them into WaveGC, multi-resolution wavelet bases plus matrix-valued kernels. Short-range tasks get sharper. Long-range graph info stops slipping through. You split Chebyshev polynomials into odd-even terms. Suddenly, wavelets satisfy admissibility strictly. No more loose approximations. You add theoretical rigor. It captures both micro and macro scales, unlike prior wavelet methods that capped at small scales. You run experiments. VOC dataset jumps 15.7%, short-long tasks all climb. You add proofs. It decouples near and far info for every node, something basic message passing never mastered. You realize you didn't build just another graph conv layer. You built a bridge between local precision and global reach, between rigid spectral transforms and flimsy approximations. This isn't a wavelet network. It's a universal translator for graph information across all scales. Okay, let's unpack that. You've just heard, well, a glimpse into the kind of pretty cutting-edge stuff we're diving into today. Our mission, really, for this deep dive is to shortcut you to being well-informed about a fascinating leap in how machines learn from complex, interconnected data. Think, social networks, molecular structures, all that jazz. We're going to explore how researchers built what they call a universal translator for graph information, and how it solves some pretty persistent headaches in the field.
Exactly. And, from a researcher's perspective, it often feels like you're trying to, well, fit a square peg in a round hole, sometimes repeatedly. For years, we've had these powerful tools in graph machine learning, sure, but each one just came with its own set of, let's say, frustrating quirks, like having a favorite screwdriver that just never quite reaches that one crucial screw.
That's a perfect analogy. You felt that frustration, haven't you? When you've got maybe two decent options, but neither one really nails the whole problem. That's exactly where the world of graph convolution was kind of stuck. On one side, you had these Fourier-based graph convolutions.
Yeah.
Solid, foundational, yeah.
Well, definitely.
But when you needed them to understand signals across a big, sprawling network, they hit walls, like you said, shouting across a canyon and only getting back faint echoes.
Precisely. They really struggled with capturing information effectively over large spatial distances.
Yeah.
And their capacity for spectral functions was just inherently limited. They couldn't get the full breadth.
Right. Then on the other side, you had wavelet networks. Conceptually, these seemed great for super fine-grained, short-range precision, almost like examining individual threads in some complex fabric. But ask them to step back, see the whole tapestry. They'd often fumble the bigger picture. Past wavelet methods just often couldn't stretch beyond the small scales.
Yeah, the core issue was really a lack of flexibility, adaptability. Existing techniques in spectral graph theory, they were powerful for analyzing graph data, for generalizing convolutions. But they always seemed to force researchers into this trade-off.
The trade-offs.
Yeah, you had to choose. Do you want diverse spaces, or do you want powerful kernels? You rarely got both integrated seamlessly. It was like having, a great microscope and a great telescope, but you just couldn't combine their views properly.
Okay, so given those limits, that trade-off, what was the aha moment? What made them think, hey, let's merge these things, Fourier and wavelets?
Well, what's really compelling, I think, is they realized these two approaches, even though they looked pretty different on the surface, they actually shared these profound underlying abstractions.
Abstractions
like how they both dealt with adapting spectral bases, how they expressed kernels, how they mixed information across multiple scales. Connecting it to the bigger picture, it was this sort of epiphany of commonality, which led to the maybe obvious in hindsight but elusive question, why not merge them?
And that merge gave us WaveGC, wavelet-based graph convolution. So it's this unified framework bringing together both the spectral basis and the kernel side of things.
Exactly.
It's not just another small step then. It sounds like a real bridge between that local precision, the threads, and the global reach, the whole tapestry.
Yeah.
A universal translator, like they said, for graph info across all scales.
Yeah.
And the brilliance, you're saying, is in two key innovations.
That's right. Two main things.
Okay, what are they?
First, it's combining these multi-resolution wavelet bases with something called matrix-valued kernels.
Matrix-valued kernels. Okay.
And second, this really clever method for actually constructing the wavelets, which involves, surprisingly, splitting Chebyshev polynomials into odd and even parts.
Chebyshev polynomials.
Yeah.
Okay, we definitely need to break those down. But first, before we get deeper into WaveGC's genius, maybe let's quickly set the stage, just a refresher. We're talking about data not as a flat spreadsheet, but as a network, right?
Right.
Friends on social media, proteins in a cell, roads in a city, that kind of thing. This is graph data. Nodes are the things, edges are the connections.
Right. And analyzing and learning from that kind of data, that's the whole field of graph machine learning. A key operation is convolution. You can think of it like applying a filter to pull out important features.
Easy enough for images, maybe?
Relatively, yeah. Images have that regular grid structure. But on graphs, it gets tricky because they're irregular. No nice grid.
So for a long time, spectral graph convolution, the traditional kind, often relied on the graph Fourier basis. You said we can think of that like a fixed set of lenses for different frequencies on the graph.
Yeah, that's a good way to put it. It was a prevalent choice, kind of the standard tool for a while.
But it had flaws. You mentioned inflexibility.
Big time. They have this constant resolution, fixed frequency modes, just not very flexible. And maybe more critically, they lack adaptability. You couldn't really optimize them well for different data sets or tasks. They often just fell short when trying to model how signals spread out over really large distances on the graph.
Like that camera with a great fixed lens, but no zoom.
Exactly. No zoom, no real adjustment.
Okay, then came graph wavelets. They
Yeah.
promised more flexibility, right? Adaptable bases.
They did promise that, but they came with their own set of challenges. Often they couldn't strictly satisfy some really important mathematical criteria.
Like the admissibility criteria.
Precisely. That one's key. Or they just weren't truly versatile across different kinds of graphs and tasks. They were better, but still not the full solution.
Which brings us right back to WaveGC and its two big innovations. Let's tackle that first one. Unifying the spectral basis and the kernel. How does WaveGC do that?
Okay, so WaveGC builds its spectral basis using graph wavelets.
Yeah.
But crucially, it allows for adaptively constructing multiple graph wavelet bases. This gives it that multi-resolution approach we talked about. It can capture info across the whole graph spectrum, close-up details, far-reaching connections, all of it.
And the filter part, you mentioned a matrix-valued spectral kernel. That sounds technical. Can you break that down?
Yeah, let's try. So think about traditional filters, maybe using vector-valued kernels. They often just scale things uniformly, like a simple volume knob.
Okay.
A matrix-valued kernel, though, it's more like having a full audio mixing board.
Ah, I like that.
You can individually tweak the volume, the tone, everything for each specific component of the signal. Or in this case, for each localized node-specific pattern the wavelets pick up.
So much more control.
Way more control. It's a significant step up from those simpler vector-valued kernels you see in Fourier methods.
Why is that extra control so important for wavelets specifically?
Because, well, a vector-valued kernel just scales global frequency stuff. But wavelet coefficients, they encode these really localized, node-specific patterns. They need a different, more granular kind of parameterization. The matrix-valued approach gives you way more learnable parameters.
Which means?
Which translates directly to much greater expressivity, a bigger capacity to learn and adapt to really complex patterns in the data.
Okay, that sounds incredibly powerful. But more parameters, more expressivity, doesn't that usually mean a higher risk of overfitting? Like the model just memorizes the training data?
That's a very fair question. And it's where their clever weight-sharing strategy comes into play. Instead of needing a unique, huge matrix for every single frequency mode, which, yes, would be massive and prone to overfitting, they figured out a way to share weights.
Share weights how?
They reduced the parameter count dramatically. Instead of needing something on the order of n nodes times d features squared, they get it down to just d features squared.
Wow, okay. That's a big reduction.
Huge. It's like having one incredibly versatile camera lens that can adjust perfectly, instead of needing, a million different fixed lenses for every possible shot.
So you keep the expressivity, but manage the complexity.
Exactly. It mitigates that overfitting risk significantly, which is always a challenge with complex models.
Okay, that covers the first innovation. Now, the second one sounds really intriguing, how they actually build these flexible wavelets using Chebyshev polynomials. What's the story there?
Right, the Chebyshev polynomials. So these are a specific family of polynomials, mathematical functions, that are really good at approximating other more complex functions.
Like mathematical building blocks?
Kind of, yeah. Special building blocks that let you create curves with very precise shapes. Now, the big hurdle in designing graph wavelets has always been meeting those admissibility criteria strictly.
The math rule that says they have to actually oscillate, right? Zero value at zero frequency.
Precisely. They need to be true wavelets, capturing oscillations, not just constant signals. And previous designs often compromise. Either they weren't strictly admissible or they weren't truly adaptive.
So how did WaveGC use these Chebyshev building blocks to crack that problem?
Their solution is really quite elegant. They approximate the necessary functions, the scaling function, and the wavelet bases by doing something specific. They separately combine the odd, even terms of the Chebyshev polynomials after a particular transformation.
Odd and even terms. Why separate them?
That decomposition is the key. After this transformation, it turns out the even terms strictly satisfy those wavelet admissibility criteria. They are perfect for capturing the oscillating high-frequency detail.
Okay, and the odd terms.
The odd terms are used to handle the crucial baseline information, the non-oscillating part, sometimes called the DC component.
Ah, so they split the job. Even terms for the wiggles, odd terms for the baseline.
You got it. And by learning the coefficients for combining these odd and even terms, they can essentially create wavelets with almost arbitrary complexity and flexibility.
Tailor-made for the data.
Exactly. Precisely tailored to the specific graph data and the learning task. It's like having a toolkit to custom build the perfect filter for any part of your data, big or small.
Okay, this feels like more than just mathematical cleverness. This design, combining the matrix kernels and the Chebyshev trick, must give WaveGC some serious theoretical advantages, right? Especially in how it handles information flowing across the graph.
Absolutely. What's really impactful theoretically is that WaveGC can effectively capture, and this is crucial, decouple short-range and long-range information simultaneously for each node.
Decouple them, meaning it can tell the difference.
Yes. It can understand local context and global context independently, but at the same time. This gives it superior filtering flexibility. Many older graph wavelet networks, they could really only verify localization at small scales. They struggle to properly integrate or differentiate global patterns. WaveGC can handle both micro and macro scales effectively.
Okay, how do they prove or demonstrate this decoupling? I saw something about maximal mixing.
Right, maximal mixing. It's a concept used to understand how much influence or information one node in the graph can mix with another node far away. Traditional message-passing networks, which are common in graph learning, often struggle here. They either mix too much,
Leading to over-smoothing, where everything just blends together.
exactly, everything looks the same, or they mix too little, and distant nodes just can't communicate effectively. It's a hard balance to strike.
So how does WaveGC strike that balance, and what's controlling it? Is it the Chebyshev polynomials again?
That's the interesting part. The theoretical proof actually shows it's not the order of the Chebyshev polynomials that controls this mixing directly. It's the scale parameters of the wavelet itself.
The scale says, like a zoom level.
Exactly like a zoom level. Think of it this way. A smaller scale, says, forces the network to use more layers, more steps to mix information between distant nodes. It naturally emphasizes short-range interactions.
Okay.
But with a larger scale is, the wavelets reach further. You can achieve the same degree of long-range mixing with fewer layers in the network.
Ah, so you can tune the reach just by adjusting the wavelet scale.
Precisely. This gives you explicit control over that balance between local detail and global communication, a level of control that many other models haven't achieved. It lets WaveGC adapt better to graphs with very different structures.
And presumably the real-world results back this up. It's not just theory.
Oh, definitely. The empirical results are quite strong. WaveGC consistently outperforms various baseline methods across a whole range of tasks. On those short-range tasks, things like node classification on standard datasets like computer or ArcB and ArcSIF, it shows clear improvements, solid gains.
But the real test is the long-range stuff, right?
That's where it really shines, yes. Those tasks that require understanding the big picture.
Can you give us a concrete example of that long-range impact?
Sure. A standout example is the Pascal VOC SP dataset. It involves image segmentation using graph structures. On that dataset, WaveGC achieved an improvement of up to, I think it was 15.7% compared to other state-of-the-art models.
15%, that's huge in this field.
It's a massive jump. It really underscores its superior ability to perceive and integrate information from very distant parts of the graph. That's absolutely critical for understanding global patterns, like recognizing whole objects in an image based on pixel relationship.
And they did those ablation studies too, where they take bits out to see what happens.
Did those confirm that all these pieces, the matrix kernel, the Chebyshev split, are actually necessary?
They did, and yes, the ablation studies confirmed it pretty clearly. Every key component, the wavelet terms derived from Chebyshev, the scaling function part, the matrix-valued kernel, proved essential for top performance. If you removed any one of those innovations, performance dropped noticeably. It really showed that the strength comes from the integrated design, not just one lucky trick.
Okay, so we have this powerful new model, validated by theory and results.
Mm.
What about actually using it? Is it practical? What are the computational costs like?
That's always the next question, isn't it? The main computational bottleneck is an initial step called eigendecomposition. Its complexity is roughly O(n) cubed, where n is the number of nodes.
Oh, okay, that sounds potentially scary for very large graphs. It can be, yes. For truly massive graphs, n cubed is computationally expensive. However, for small to medium-sized graphs, it's perfectly practical, especially in domains like molecular analysis or certain types of image processing where that detailed spectral modeling WaveGC provides is really valuable. The accuracy gain might be well worth the upfront cost.
And I think you mentioned they have workarounds for larger graphs, too. Something about randomized SVD.
That's right. For larger graphs, they can use approximation techniques like randomized SVD. This brings the complexity down significantly, more like O(n) squared log k, where k is related to the number of eigenvectors you approximate.
Much better than n cubed.
Much better. Plus, remember, this eigendecomposition, or its approximation, is a one-time pre-processing step. You do it once before you even start training the model. And the time it takes is consistently reported as being less than the actual model training time itself.
And is that the end of the line for optimization? Or is there potential to make it even faster?
There's definitely potential. The research points towards further developments, particularly using a fully polynomial-based approximation. The idea there is to potentially remove the need for any explicit eigendecomposition altogether.
Which would bring the complexity down to...
Potentially down to O(n), linear time. That would make WaveGC incredibly scalable, suitable for even very large graph datasets in the future.
So there we have it. It started with this real frustration, right? Models hitting walls with long-range signals, fumbling short-range precision. And it led to WaveGC, this genuinely innovative solution that really does seem to act like a universal translator for graph information, skillfully bridging that gap between local detail and global reach.
Absolutely. And I think the ability to effectively capture and, importantly, distinguish between information across all these different scales, it's not just a neat technical trick for AI. It fundamentally changes how we can analyze and pull insights from any complex network system, thinking about biology, social science, engineering. The potential applications are huge.
It really makes you wonder, doesn't it? What other crucial connections, what other breakthroughs are just waiting out there? Simply by looking at old problems, old trade-offs, through a new lens and asking that simple question, what if we merged them? This deep dive into WaveGC really confirms, for me at least, that the future of machine learning isn't just about building bigger and bigger models. It's about building smarter ones, models that truly understand the underlying fabric of the data they're learning from. We hope this deep dive has given you plenty to chew on and maybe sparked your own curiosity about what's coming next in the fascinating world of graph AI.